I'm so stoked to be here. My name's Aaron. I'm the CEO of a company called Rossi Corp. And this is actually my second time at Local-First Conf speaking. I have a completely perfect record of speaking at Local-First Conf. So, and last year, I was really excited to be here because we announced for the first time that we are working on this new sync engine that we call Zero. And at the time, it was just an announcement. You couldn't use it. And the key idea of Zero is this concept that we call query-driven sync. And this is a snapshot of me at that point in the talk. And the key question, like the key idea in Zero is like, you can't sync all the data in most applications to the device. That doesn't make sense. In existing sync engines, including our own previous sync engine, Replicache, there's ways to partially sync data, but it's a lot of work. You have to manually configure it. It's fairly static. What if you didn't have to do that? What if you could just write queries in the front end, and that drove what data got synced to the client? That's like the key idea. And since the announcement, and actually for, I don't know, months before that, 9 months before that, we've been working on this. We launched it in alpha in December. And it's live now. You can use it. And so the key idea has remained the same. Zero works with a concept called query-driven sync. The syntax has changed a little bit. You might notice before we had joins, we replaced those with first-class subqueries using the related keyword. But basically, you write an app, like a classic SPA. You get a client-side query API. You do these queries. The result comes to your browser, just like any normal client-side query language. Then the queries sync continuously, reactively, as the data changes. But the key idea is that when you do a new query that overlaps with a query that you've already done, the data is serviced directly from the local device. So it is a sync engine. It's reusing data on the local device for reads, so you get instantaneous reads. It reuses data on the device for writes, so you get instantaneous writes. But the data that is synced to the client is completely driven by these queries. So today, I'm going to talk a little bit about how this works. I hope to go into a fair amount of detail. I hope it's not too much detail, but we really had a lot of fun designing this and building it, and looking forward to sharing more about how it works. So this isn't the whole architecture of Zero. This is a slide that shows the architecture of just the query-driven sync system. There's no writes here. I'm not going to talk about writes today. So on the left, we have your client, which is a SPA web application. In the middle, we have a server. This is not your server. You still have an application server in the Zero architecture. It's not pictured here. This is a specialized syncer server, like a sync server. We call it Zero Cache. And then on the right, you have your database. And at a high level, the server, Zero Cache, tails the database. It consumes the replication log for the database, populates a replica on the server, and interacts with the client for sync. And I'm going to walk through how this works in some detail as a substrate for what we're going to talk about later. So I'm going to walk through like sort of the life of a query and how it gets synced to the client. So it starts out, the app registers a query with Zero, with the Zero client. And this query is a reactive query, just like many other sync engines. So if the data there's a data store in Zero on the client, and if the data store changes, this query will reactively update, and it will update the app. So that's just like previous sync engines, no different. But what's different about Zero is that once the client registers this query, we take that query and we send it to the server. And it runs reactively on the sync server too. So we have a similar reactive query model on the server. We have a similar data store on the model, or on the server, and the query runs reactively there too. So if we're walking through the life of a query, we say that this is the very first query that's run on this app. That first time it ran, it will get no results, because there's no data in the client yet. So the query runs once, it returns an empty result. The user sees a blank page for a second. The query gets sent to the server. It runs on the server. It finds data in the data store, and it returns the rows that are necessary to represent that query, the resulting rows, to the client. And it's important to note here that the server knows for every client what rows the client has at all time. It has precise track of the rows that are on each client. So it sees like, okay, this query resulted in whatever these 100 rows. The client has no rows right now, so we're going to send those rows to the client. They go into the data store. Of course, because the client queries are reactive, that modifies the data store. That causes the queries to rerun. That causes the app to update. And the user sees the first screen of the page. So if there's an update, like let's say there's a write to the database, an interesting thing is that Zero doesn't actually care how the write to the database happens. It can happen because you went into SQL console and changed a row. It can happen because the app did a write like in the UI, or it can happen because some LLM talked to the database or whatever. But somehow the database changes. That causes database replication to happen. It goes into the replica on the server. That causes the data store to change. That causes the reactive query to rerun. That causes us to calculate what rows are different for this client. We send those rows to the client. That causes the client data store to change. That causes the client reactive queries to rerun, and the app updates. And that's sort of the life of a reactive query in Zero. So this has a lot of cool benefits. And I'm going to walk through a few of them. So the first one is partial sync. That's what I opened with, and one of the key reasons that we investigated this approach. For most of the applications that our users want to build, it's not practical to download all of the data onto the device. This is like a key consideration. This is why we started Zero. If we think about, when we talk about partial sync in Zero, we often say that queries start on the client and they fall back to the server. But that's just like a lazy, colloquial way to describe how the system's working. It isn't really true, and it's cool to see how it's actually working. But we think through that model that I just described. When the app starts up, most Zero apps do what we call a preload query. We don't have a special notion of preload in Zero. It's just what we call queries that are designed to run at the beginning of app startup and warm the cache. But most apps will do some kind of preload query where the developer chooses some set of data that they think is most likely to be needed by the app in the future. Sort of the 80-20. What's the 20% of data that's going to cover 80% of the needs of the app? So the developer will cause the app to do a preload query. That query will run on the client. It'll, of course, get no results initially. It'll get sent to the server. It'll run on the server. It'll get a bunch of results. Those rows will be sent to the client. And then the app will render. So now let's say the app does a new query. The user navigates somewhere. And let's say the developer did a good job, and they chose a preload query that covers this navigational query, N1. We'll call this query N1. So again, the navigational query will run. It will get registered on the client. It will get sent to the server. The server will run the navigational query. And in this case, the server will find out, there's no new rows. This navigational query does result in rows, but those rows are already on the client, so there's nothing to do. So it sends nothing to the client, and the client, by this time, has already navigated because the reactive query ran, and it also found rows the first time. And so the user navigated instantly. But now let's say that the user navigates someplace new, to a place that wasn't covered by that initial preload. And to make it interesting, let's say that they navigate to a detail page, and the client data store has some of the data, but not all of it. Let's say that it has the title of the detail page, but it doesn't have the body. What will happen is the query will run on the client. It will get some results. Those results will return to the app immediately. The app will navigate instantly to the new page, but there will be an empty place where the data is missing. That query will get sent to the server. It will run on the server. It will get the full results, and the delta rows will get sent to the client, which will cause that original query to rerun again, and the user will see the complete page. So it isn't really true that queries are running on the client and then falling back to the server if there's no results. What's really happening is that queries run in both places all the time. All queries run on the client, all queries run on the server, and the user's perception of what's happening is that this fallback is happening. So another thing that this enables is read permissions. This is another thing that when we were working on Replicache, our previous sync engine, we got this problem from our users over and over and over again. Almost every app that our users want to build have some kind of fine-grained read permissions. Think about Notion. You can share a document with just a subset of people. Think about like a project management tool. Maybe you have a special project that has only certain team members have access to. People were struggling to build real applications with Replicache because there was no fine-grained read permissions. The way that query-driven sync handles this is that the developer registers with the server ahead of time permissions. And these permissions are just where clauses to a query. You can think about the kinds of permissions that you'd commonly want to use, like someone can access a file if they're the owner of the file, if they created the file, if they've been explicitly granted access, if they're in a group that has access. All of these can be expressed with queries. And you can think of it as like a user can access a file if they are the owner, or the user can access files where they are the owner, or they have access through a group, or they've been explicitly granted access. So they're basically just where clauses, and that's how we represent them. We have a way for the developer to register permissions ahead of time for each table, and they express them in where clauses. So when a client issues a query, say select all documents, what really happens is that query, select all documents, gets sent to the server. The server looks up in this permission system the permissions that should apply to the documents table and adds them as where clauses to that query. So the system ends up running two different queries, one on the client and one on the server for the same logical request. And so the query that ends up running on the server is like select star from documents where blah, 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 blah. And only a subset of the rows get sent to the client. The client continues running the original query naively, not knowing that it's only seeing a subset of the data, and everything just works. And the final thing this enables is fast page loads. A thing that people frequently told us with Replicache is that they wanted the benefits of sync, instantaneous user interactions, full reactivity, but they still wanted to be able to enable certain pages on their app to load really quickly. Because think again about Notion. Mainly you use Notion within your org, and the people that are participating are long-term users that it's okay for them to have a slower startup and to get more data. But you can also, with Notion, build fully public experiences that anyone on the internet can just drive by and see. And those people shouldn't have to wait for the entire database to download before they can see the page. So you can build this with query-driven sync just by assembling these queries. As I said, there's no specific notion of preload. They're just queries that you run at App Startup. And because you have control of this, you can decide when the user loads this publicly visible page to sync just the data for that page. And then after that loads and the app comes up, then in the background, maybe you sync more data. If they go to the list page, you'll be ready. And maybe even after that, you sync even more data so that if they do a search, that'll be fast. So this basic mechanism of synchronized queries gives developers control to build whatever partial sync experience that they want. It's not like Zero has partial sync built in. It's just that we have primitives that enable you to build it in your app. So we had this idea to build Zero long before we actually started building it. But the reason we didn't do it is because we couldn't figure out how to do it. And I'll try to illustrate why quickly. If you think about building this system, the sort of first thing that comes to mind is to use a traditional database. Zero is designed, and our previous sync engine is designed to work against existing standard databases like Postgres. And so if we look at this diagram, maybe we'll do these reactive queries just using standard SQL queries. Well, that won't work at all. And the reason why is because, one, these queries are huge. The whole point of using a sync engine is to get a significant amount of data onto the client. In Zero, we actually only want tens of megabytes of data on the client because we have partial sync, so we can fall back. So we don't need to have a gigabyte of data on the client. But still, if you think of a normal SPA, you navigate into a page, it's gonna how big are the queries that it's gonna do? Maybe 40K. So if you're trying to sync 20 megabytes of data, it's a 100 times bigger query maybe. But not only that, the queries are complicated because they're enforcing permissions. They're usually doing subselects so that they can get related data. So these are expensive queries. They're big queries. And the worst part is that they need to rerun constantly. Because if you're trying to get this reactive experience where if something changes, oh man, there's a typo. You're trying to get this reactive experience where the queries update live. Anytime, the whole point is that the data you have on the device is the data that users are using, right? So that means that any user who's looking at the app at the same time as you who changes anything is going to cause every other user to rerun their queries. So that's an n-squared problem. It's obviously not going to work. So the first thing you might think about is OK, fine, we'll use normal queries, but what we'll do is we'll only rerun the queries if they're invalidated, if they're dirty, right? Maybe we can detect if a query is dirty, and we'll be really careful about that, and we'll only rerun it when it happens. Well, first of all, that is a famous problem called the invalidation problem, and it's very, very difficult. It's like an open research problem, so it's difficult to do well. But OK, maybe you'll use some heuristics and you'll get close enough. But the bigger problem is invalidation doesn't work at all. It's actually a useless approach. Because again, the whole point here is to get data onto the device that the users are likely to use. So that means that this data is going to constantly be changing, and it will actually be invalid. So we can't just rerun the queries. We can't use that. So this is kind of a bummer, but luckily there's been a lot of recent research on this. It's true that you can't use a normal, classic, traditional database, but there are new research databases, new as in the last 10 years. In databases, time moves slow. And so there's new research in the last 10 years of novel databases that have what's called incremental view maintenance built in. And these have turned into products. There's a product called Feldera that's based on this DBSP paper. There's an open source database called Noria that's based on this paper. There's a company called Materialize that's based on a different paper that's not on this slide called differential data flow. And so there's been work on building databases that incrementally update queries efficiently. And there's published papers on how to do that. So we thought, OK, let's try to use one of these papers and build this system out of this kind of incremental view maintenance. And the first thing we looked at was we tried to build this using this one, DBSP, because this is actually the newest of these papers. But it's based on differential data flow, which is a simpler and older version of this idea. And there's nothing really different for our purposes here today, so I'm going to illustrate this using the problem that we found using differential data flow. And I want to explain how this works, because it's the basis for how our system works. So the key idea, differential data flow is really cool. If you have any interest in this stuff, I cannot recommend highly enough looking at the papers or the open source projects that implement this. It's a really beautiful idea. And the basic idea is that you take a query, in this case, maybe our query is we're going to get all albums where the title starts with foo. We're going to get the related artist. We're going to order it by publish date descending. And we're going to get the top 10 of those. Simple query. The way differential data flow works is you take that query and you break it down into a graph of what are called operators. And you build essentially a data pipeline out of it. So data sort of comes in on one side, it flows through the pipeline, and it pops out the right side. And the things that are flowing through the pipeline, they're basically changes to the database. So that's why we've got delta album. This is a change to a row added, or an album row added, an album row removed. We've got artist album added, artist album removed. And at the end, what pops out is a change to the query result. So this is a much more efficient way to update these kind of queries. You can get updates to a query that are much cheaper than rerunning the query from scratch. So basically, the way it works is to start up, to get the initial result of the query, we just treat all rows as additions. So if we want to calculate the initial result for this query, we take all the albums, we push them through the data flow one at a time. For each album, we check to see does the title match the filter. If it does, it comes down here. And what happens in the join operator is the join operator keeps a lookup table, essentially, of both sides of the join. So it keeps like all the albums in a lookup table by artist ID. It keeps all the artists in a lookup table by ID. And when the album comes in, it looks and sees like, OK, is there a match? And since this is an inner join in this case, if there's no match, there should be no result in the query. So in that case, it will drop it. And so we push all the albums through. They all do the same thing. They like get to the join. They look and see if there's an artist. There's not, so they stop. It's actually kind of an interesting thing with these things. It doesn't matter what order you push them through. So you could push all the albums first, all the artists first, or mix them up. But anyways, like say we do all the albums first, then we do all the artists. The first artist we'll get here, it will look for albums that match in the lookup table. It will find some, and it will push those through to the next operator. Then in the top K, we have basically another data structure. It's like a sorted list of all of the rows by the sort criteria. And then we manage the window and push out the results. So we experimented with using this, and we hit like a pretty significant problem. And the problem is hydration performance. The basic idea here is that you're going to push all rows through the pipeline. And so this kind of like, it isn't always I think there's some optimizations you can do, but the basic idea is that you are going to have a time to materialize of like roughly the number of input rows. And you're going to also have state in the system of like roughly the number of input rows. So I think this is like a reasonable approach for like these systems have found a lot of popularity in like backend databases where they're basically used for like OLAP queries. Like you have some query that you're running for years, and it costs a long time to start it up once, but then ongoing it's very, very cheap to run. But like what we want to do with Zero is like interactive UI, like like building linear or building like Notion, And so we're constantly running new queries, and these queries are like on screen for like seconds, So having this really extreme hydration performance just didn't seem workable to us. So we looked at like a lot, like how can we change this? How can we adapt it for what we're doing? And we came up with something somewhat new, somewhat inspired by other projects. And I usually call it ZQL, but Matt on my team is saying we need to give it a different name because we call the query language ZQL. So we're experimenting with ZVM, Zero View Maintenance. And the way it works is it similarly breaks down the query into a graph of operators. But what's different about it is that it has a fetch phase. So at the beginning, when the user first requests data, instead of pushing all data through the pipeline, we actually pull the data from the bottom. And the reason that's important is because unlike other systems, our data in this system is sorted from the beginning. So the inputs are sorted streams. And so because we're pulling the data through the pipeline, we can stop early. So like at the very, very top of the pipeline, we have like albums sorted by published descending, and artists sorted by ID. So what that means is if we're doing a query by published descending, we have the source data in the right order. We can pull it through the pipeline in the right order, and we can stop when we're done. So this makes hydration a lot faster. It's basically the way that like normal database query engines work. The difference is that once hydration is done, it transitions back into a push mode, and then pushes work as in other IVM systems. The neat thing is that like because we have fetch built in, we actually don't need state in the operators. So like neither the join operator nor the top K, we call it limit, operator needs to have state in it because it already knows how to fetch data from upstream. So it can, when we pull a row through here and we need additional state from the artist, we can just get it at that time. I'm going to have to go a little faster because I want to show a demo. OK, so we wrote a little program using the same data model, using a Rust implementation of differential data flow. So this is, and please excuse the output here, it's so ugly. I spent literally 4 days like fighting with Rust. I hate Rust. Sorry, any Rust lovers. Can't teach old dogs new tricks. Anyway, so this is running over 25 megabytes of data, a 25 megabyte data set. It's like all albums from the 90s. And what it's doing is finding all, you can put a filter in. It finds all albums that start with that filter, case insensitive. And as you can see, the hydration took about 100 milliseconds. So like 100 milliseconds, that's, I guess it's not that bad. But again, it's 25 megabytes of data, so it's a very, very small data set. And actually, like because of the way like differential data flow works, it actually has a huge advantage when it has a filter because it's pushing less data through the join and less data through the limit. So if we take out the filter, it actually gets worse, sadly. And it takes about 2 seconds. It's possible that, like I said, I'm not the greatest Rust programmer, so I think there could be some optimization here. But like the basic thing I'm trying to communicate is that the basic setup of this system is that we're pushing all the data through the pipeline, and it's non-ideal for hydration. So we implemented that same program using ZVM in TypeScript. So this is actually Rust versus TypeScript. So Rust has like a 10x advantage like right off the bat. And can see it hydrated in 3 milliseconds. And if we do a new query, we get hydration in roughly 1 millisecond. And we can do updates, incremental updates still. And they're pretty fast, half a millisecond to do incremental update. So this is just like a demonstration that this basic approach, I think, is a better match for the trade-offs that interactive applications need. Okay, so we started Zero with the idea to build general purpose sync. Like, our big picture goal with the product is sync builds really, really great user experiences, really fast user experiences where everything is reactive. But until now, the number of applications that are matches for sync is very, very small. It's like a tiny niche of applications that you can realistically use sync for. And we wanted to build a sync engine that was general purpose, that can address a much wider variety of applications. So there's like this question, like, did this work? Query-driven sync, is it an answer to this problem? Do you get, does this approach to IVM work? And I have an answer to that, but like one way to answer that is with this app we made, ZBugs, which is a dog food app that we built for Zero when we launched it. Actually, we've been working on this ever since the beginning of Zero. You can actually load this if you want. This is our real bug tracker that we use for the project. We built this dog food app because, does this mean I'm over? Yes. Oh, crap, okay.